Hello friends, welcome to my channel. Let's have a look at problem 2366, minimum replacements to sort the array. So in this video, we're going to share a solution based on transforming the problem to a standard optimization problem. Then writing the code is a piece of cake. So in this problem, we are required to return the minimum number of operations to make the array in sorted order, in a non-decreasing fashion. So in that operation, we can replace any element of the array with two elements that sum to it. For example, in this example, we can break 6 to be 2 plus 4. So here are two examples. So in example 1, so we break 9 into 3 copies of 3. So the total number of operations needed is 3 minus 1, that is 2. And in example 2, the array is already in sorted order, so the return is 0. So let's also look at the constraints. The first constraint is that the length of the array can be up to 10 to the power 5. So in other words, we cannot use pure brute force, for example, a square term complexity solution. The second item is not that essential in here. So with that said, let's look at the method. So here we are going to solve this problem by transforming it to an optimization problem. So once the problem is abstracted to a model problem, solving it is very simple. The procedure is as follows. First, we are required to make the array in sorted order in non-decreasing fashion. So we are going to look from right to left. So if we see current number is larger than the element to its right, so we need to break this current number. The question is how to break. So please see below for the strategy. So next is that during the process of the above linear traversal, we're going to update the count of operations needed. So here we want to transform the first part into a model problem. So once we isolate the situation, then things should be very clear. So given a reference corresponding to the right elements above, and a current number y, so y, let's assume y is no less than reference. So we would like to break y into key numbers such that these key numbers sum up to y. And let's assume that this a1 and up to ak is put here in sorted order. So just for convenience to fix the idea. In other words, A1 is the smallest and AK is the largest. So we want the largest one, AK, is bounded above by reference, and the smallest one to be as large as possible. So actually the requirement A1, the smallest one, to be as large as possible induces that we want the K to be as small as possible, right? So the strategy is the following. So if we do not do deeper analysis, maybe we think try to break y into copies of the reference. So that's right in some sense, but not all. So let's assume y divided by reference equals k. That is the integer part. So we are going to use this to fix the idea. So first, if the reference divides y, then we could use the key copies of the reference. So these key copies sum to the y, and the smallest is the reference. So that's totally fine. That's the best strategy. In the other case, if the reference does not divide y, so we need to break y into k plus 1 parts. If we use smaller parts, so the largest one will be larger than the reference, right? And also we claim the smallest one possible, the largest possible smallest a1 is y divided by k plus 1. Let me restate this. So the largest possible a1 is this number, y divided by k plus 1. So this can be easily proved by contradiction. So assume that the smallest one can be larger than this number, because we are considering integers, so a1 is at least this number plus 1. Then if we consider the sum, because we need at least k plus 1 parts, so we sum a1 up to k plus 1. So what we get is this number plus 1 times k plus 1. So, the first one gives almost y, but then we have a k plus 1 factor. So this in total is always strictly larger than y. So that's impossible. In other words, the largest possible event is this number. So here is an example. For example, if we have a reference that is 5 and y is 11, so we need 11 divided by 2 by 5, that is 2, plus 1 terms, that is 3 terms. So this is one decomposition and this is another decomposition. We are going to use the second decomposition because the 3 is larger than 1. So here is an example walkthrough. So this is a array. So we are going to scan from right to left. So here, here, here. Then we see 7 is larger than 6. We are going to break 7 into 2 parts, right? So we can break 7 to be 1 and 6 and 3 and 4. So we are going to use 3 and 4 because 3 is larger than 1, right? So after this break, we have 12, 9, and then 7 is break into 3 and 4. So the current smallest is 3 to the right of 9. Then we see 9 is greater than 3. So we need to break the 9 into 3 copies of 3. So we need 2 operations. So after the break, we have 12, and the right of 12 is 3. Then we need to break the 3 into 4 copies. We need to break the 12 into 4 copies of 3. So we need 3 operations. So in total, we get 1 plus 2 plus 3, that is 6 operations. So after the break, the smallest number in the array is 3, right? So that's the walkthrough. So if we absorbed the strategy above, then writing the code is actually a piece of cake. So first, let's do a reference that is nums -1, the most right element. Then we track the length of the nums, let's call it m. Then we're going to look from right to left, so for I in range. So the second to last index is n minus 2, and we are going to end at 0, so we write -1 here, and the increment is -1, meaning that we scan from right to left. So the current reference is given by the last number in the array. So we do this check. If nums I is less than or equal to the reference, so it just continue, right? Nothing to be done. So if it's strictly less, so we're going to reset the reference to be nums I. So outwards, just continue. So this is the one case. Otherwise, we're going to consider the relation between the current number, that's nums I, and the reference number. So if R equals 0, so it means that we can divide the current number I to be a Q copy of the reference number. Then we need to, let's set a result to be 0 for counting. So we're going to increment the result by Q minus 1. And then in this case, the reference does not change, right? So that's it. So in other words, in other case, if R is not equal 0, so we split this into Q plus 1 parts. So the increment in operation is Q. And after the split, the smallest number is the following. So is nums I divided by Q plus 1. We shall use this number as the new reference, right? So after this, so we are ready to return the result. Now let me make some remark. So this corresponding to the first item in the strategy, and this one, a second item in strategy, right? So with that said, let's do a special case check. Yeah, it passes the first example, or the example we cooked up. So now, so this is actually also a test case for this problem. So next we do the generic case check. So yeah, it passes all the cases. So here actually, we write this in a such format. for the purpose of fixing the ideas. So actually, for this one, we can absorb this and this together, in other words, to make the code shorter. But I feel that this way of presentation is better for understanding. With that said, I guess that's about it. Thank you very much.